Hello and welcome back. Today's algorithm is a follow-up to the latest episode, linked list circle detection. If you haven't watched that one yet, I recommend checking it out first because today's content builds on the fast and slow pointer. So let's look at the problem. The problem statement is a bit long, but in short, given a linked list that has a circle, and find a node where the circle begins and return that node. So in example 1, the entry point of the circle is node 2. And in example 2, the entry point of the circle is node 1. So here's the answer. The problem itself is easy to understand, but the solution is not obvious. Before we get to the correct solution, let's look at a common mistake. Last time we used a hash set. We use a hash set to detect whether a circle exists. So for this problem, can we just use a set again? Some of you may think I will travel the list and store each node in the set. The first node that appears twice, that must be the entry point of the circle, right? So what's the problem here? The issue is space complexity. It's O(n). So the real challenge of this problem is, can you find the entry point using only O(1) space? So while using a set does work in some cases, it doesn't meet the advanced requirements. What you really need to master is the math behind the fast and slow pointer solution. And that is exactly what we are covering today. So let's delete this. If this is the first time seeing the problem, the solution is definitely not obvious because the correct approach is actually a math method. And let's draw a simple sketch to help us analyze it. So this is a linked list and this is a circle. Yeah. And this is the entry point of circle. Let's call it entry here. And the distance from the header to the entry point, this distance we call it x. And the x is exactly what we are trying to find. And there is another key point, the point where the fast and the slow pointer meet. Let's call it pointer P. And distance from the entry to point P, let's use another color. So here is one, we call it A. And the distance from the point P back to the entry, we call it B. We use another color. So here it's B. And the total length of the circle, let's call it L. Obviously we have L equals A plus B. Now, what's the relationship between this distance? From the previous step, the circle detection step, we already know the fast pointer moves twice as fast as the slow pointer. So we have fast equal twice slow. And first, the distance traveled by slow pointer is obvious. Slow equal x plus a. So that's this one. Okay. And the distance of the fast equals to x plus a plus n times l. So something like we have maybe one lap or multiple lap stop back here. That is fast. Pay attention here. The n times L is important. N represents the number of actual laps that the first pointer made around circle before caught up to the slow pointer. It is easy to just write L here instead of NL, but that would miss the multi-lap cases. For some examples, the result may still look correct, but in special cases, it will fail. We will come back to this point later. So based on fast equal 2 times slow, we have x plus a plus n times L equals to twice x plus a. And simplified, we have x equal n times L minus a. What does that mean? This still isn't very intuitive. Let's substitute with a equal L minus b. So we have x equal n L minus b, which equals to n minus 1 times L minus b. So what does this equation tell us? Let's look at the case when n equals 1, then x equals b. That means the distance from the head to the entry equals the distance from the point P back to entry. Okay, this one equals this one. For the case when n is bigger than 1, it's simply b plus 1 or more full laps around the circle. So that means the distance x equal b plus 1 lap or multiple lap. This equation leads us to a core conclusion. If we send a new pointer from the header, let's call it third. At the same time, we let the slow pointer continue from the point P, both moving at the same speed, and they will eventually meet. And the node where they meet is exactly the entry point of the circle. Now that the solution is clear, let's see it in action with Algo Demo. Now we slow down. The first step, we need to find circle. So we use fast and the slow pointer. And we can see the fast and slow pointer meet at the node 9. Now we create a new pointer. Let's call it third from here. Start from header. You can see the third pointer, the color of third pointer is red. At the same time, the slow pointer continues from point P. And both pointers move together. We keep going. Eventually, they meet at node 6. And 6 is obviously the entry point of circle. That was the case when equals 1. Now let's look at the case when n is bigger than 1. Yeah, this one. Let's see the first step. Okay, in this example, the fast and the slow pointer meets at 9. Actually, 9 itself is already the entry point of the circle, but that doesn't affect the algorithm. So let's continue. The third start from header and the slow pointer continue from the 9 point. And continue moving. We can see the slow pointer moves 1 lap and 2 laps. and they finally meet at 9 again. Here, n equals 2. That means the slow pointer made 2 actual laps around circle before meeting surge. Do you remember what I mentioned earlier? We need to pay attention to this NL. In this case, if we had out the n in the equation and we just use x equals b, then in this test case, the conclusion would be fall apart. Because here b is either 0 or equal L, which is 4, but neither of those works for this example. So this is exactly why we need to include n in the formula, as I said before. Alright, that is for today's algorithm. Okay, the demo you just saw that was made with Algo Demo. It's an algorithm visualization app I built personally. It covers a wide range of common, frequently asked, and popular algorithms. You can step through the code line by line and watch how the data structures and the variables change at each step. You can also drag the progress bar backwards to review any part you missed. The code is highlighted at real time, and you always know which line is being executed. The download link is in the description. Okay, see you in the next one.